But I would say I'm just going to go through this whole practice exam, every question. So 50 questions. We'll kind of go a bit fast today, but I'm recording everything, so you can go back and you can look at the recording. I'd encourage you not to watch this video or remember anything from this class if you haven't taken the practice exam. Okay, so go take it as fresh as you can, and then when you get stuck or if you get something wrong, then go to the video. Or in fact, I don't have the answers in the PDF, so you got to do the test and then go through the video and see if you got it right or not. Okay, so we can go through it that way. But try to make it as intellectually challenging as possible for yourself, okay? Because you don't want to fall into confirmation bias. You don't want to say, I know from the video that answer B is the correct answer. And so you look at it and you look at the question, look at B, you don't engage the brain, you go, oh yeah, that makes sense. I know that. And you go on to the next one. If you didn't come up with it on your own, you probably don't know it. So don't get a false sense of confidence, right? So try to take that test cold and then go to the video and walk through and say, oh, I screwed that up, and you learn from your mistakes. So let's jump in. So here we are, group elements in group 7, and then it's kind of chronological in the semester. We start out with the things we did farthest to go, the naming and everything like that. And so group 7A is known as what? So what are the different names of the groups? Okay, so group 7A, and on our chart over here, it's the Roman numeral 7. What are those called? Fluorine on down. Halogens. Very good. So it's the halogens, group 7A, or Roman numeral 7. And then you have the chalcogens, that or alkali metals. That's group 1A. Over here, alkali metals. Then the alkaline earth metals. Then get over there to the chalcogens. That's group 6, oxygen, sulfur, etc. And then the noble gases is group 8. And then I only had 5 answers on there, but there's a 6th group. What's that other group that it's in our notes? It's a weird one. Pnictogens. Yeah, it starts with a P though. So that's a weird word. So that's the pnictogens, group 5. That's the nitrogen group. Don't ask me where that word came from. I could look it up. Okay, then this one. What compound is formed by strontium ions and nitrogen ions? So the most common ion for fluorine is F-, oxygen, FO2-, nitrogen would be N3- if you're just making an ion with nitrogen. So it's going to try to get to that noble gas configuration. So I have N3-, and strontium is over here in group 2. Its the shortest path to a noble gas is to lose electrons, so it can wrap around. So if it loses 2 electrons, it ends up looking like krypton. So Sr2-, N3-, we do that crisscross, right? So we want to make them compatible with each other, and so we have this 3- here and 2- there. The most common thing between the two would be 6, and so we need 3 times 2 and 2 times 3 would give us 6 pluses and 6 minuses, and that would be the neutral compound. So it would be S3N2. Okay, mercury. Here's the name of this. It's just asking you straight up, what's the name of this ion, the Hg2 2+ ion? This is like the most confusing one if you haven't memorized it, right? Because you're looking at that and you're going, what on earth? It'd be real easy to say mercury 2, but it's not mercury 2. It's a polyatomic cation. So each mercury has a +1 charge because there's 2 of them. And so we have the mercury 1 ion. So that's the mercury 1 ion. Okay, and then the correct name for aluminum oxide here, this Al2O3. This is another one where you have the 3 and the 2. So the crisscrossed, we need 2 of the Al3 pluses and 3 of the O2 minuses. Plus, aluminum is always 3+, so we don't need a Roman numeral. So again, there's really no way to figure that out. You just got to memorize which ones need the Roman numerals and which ones don't. Okay. Make your flashcards. You've got a lot of time between now and the final, so you can relearn it if you haven't. Okay, Fe2O3. So iron is if let's say I don't know, it could be iron 2+, it could be iron 3+, right? Iron makes 2+ and 3+ ions. Okay, but I know oxygen always makes a 2-, and I got 3 of those. Okay, so I know this, and I know this, and so this is the only one I don't know. I've got to figure that out. Okay, and the only way that works out is going to be if iron is a 3+. So we have the iron 3 oxide. So that would be the name for that one. Then we get to CCl4. So that's not an ionic compound. It's an organic compound. Our carbon's bonding to 4 chlorines. It's also all of those in the upper right-hand corner, those non-metals bonded together. If you have those, you have what we call a molecular compound, not an ionic compound. So everything we've done up above, 1 through 5, those were binary ionic compounds. They have cations and anions. Whereas this one is a covalent molecular compound between nonmetals. And so that's when you use the naming prefixes. So you got to know these prefixes, mono, di, tri, etc., all the way down to 10. The most common ones, obviously, are the top 4 or 5, but it's good to know. So this is carbon. The first atom is just listed as its atom name, carbon, and then you use the prefix tetra, because there's 4 of them. And then you put "ide" on the end. That's just the naming convention. So then let's do that with PF5. So that'd be phosphorus pentafluoride. So there's 5 of them. Okay. Any questions on those so far? Just again, you just work your naming, know your cations and anions. Okay. All right, some more naming and formulas. So the formula of ammonium nitrate. So ammonium is one of those memorized ones. It's NH4 right here. And so if we don't, like this one is completely out. That's not ammonium. So it's not that one. And we know that the ammonium is a +1. And this is ammonium nitrate. So we know nitrate is NO3 and it's a -1. So we just need 1 ammonium and 1 nitrate and we'll be happy. So here's what we have right there. NH4NO3. Okay, then perchloric acid. So here we have the perchloric acid. So we need this IC, that comes from an 8. So we need a perchlorate anion, and we need to just cancel all the negatives with protons. So here's the perchlorate anion, and we have 1 negative, and so we're just going to put an H in front of that, an H+. So we have an H+, canceling out that negative, and so we have HClO4. So we find that right here, HClO4. Now, when it's just a binary acid, so hydrogen added to a single element, we take that anion bromide. Okay. And in fact, I've got 2 right answers here. I don't know what to do with that, but HBr is again from bromine, Br-. So that's what we're going to get. It's HBr. So I need to go and check that test. Does it have, on your version, have 2?
Yeah.
And I'll tell you what, I copy paste all these things, and I think I'm going to copy it, paste it, and change it. And I don't know what happens to my brain. I don't change it. Okay. Bad. Okay, what's the correct name for Cn-? It's the cyanide. That's straight up memorization question. Easy 2 points. There'll be 50 questions on the test, just like this one. And so that's an easy 2 points if you've got it memorized. Now you can take that cyanide and you can add a proton to it. And cyanide is named as kind of like a monatomic one, like bromide. So if bromide made hydrobromic acid, cyanide would make hydrocyanic acid. And so that's where we get this correct answer, hydrocyanic acid. I had a lot of fun making up the fake answers for this one, like carbonitrous acid, never heard of that. hydrocarbonitrous. These are all totally fake and made up. They don't have any connection to reality. And so, yeah. Nitrogen carbonic acid, yeah, none of those. That was fun to do. Okay, so that's all the naming. Like 12 questions of naming different cations and anions and things. You say each of them's only 2 points, but right here, that's 24 points. If you don't know any of the naming, and you've thrown away a lot of easy points and a lot of fast points. You know, if you can knock these out, then you got plenty of time to do the calculations. Okay, the empirical formula of a compound with 12 carbon atoms, 14 hydrogen atoms, and 6 oxygen atoms is, and you can write that formula as C12H14O16, like right here. But if you look at all of those, they could all be divided by 2. They could almost be divided by 3, but the 14 kind of screws that up. But we could divide everything by 2 and end up with C6H7O3. So the empirical formula is the simplest ratio of all of those, where it can't be divided by anything else and still get whole numbers. So it's that simplest whole number ratio. And that's what an empirical analysis would give you. Now, if we knew the molecular weight, we might be able to come up with the molecular formula. So here's the molar mass of this CH2, this carbohydrate compound. What's its molecular formula? Okay, so the formula, the weight of this empirical formula is 30 grams per mole. So we added this up. So we had a carbon plus 2 hydrogens plus an oxygen. That's 12 plus 2 plus 16. So that's 30 grams per mole. And the empirical formula is just going to be multiplied by units, like 1, 2, 3, 4. So it's going to be multiples of 30. So to make a molecule, a carbohydrate, it's going to be 30 or 60 or 90 or 120, you know, all the way up. All your sugars, all your starches, they're just some multiple of 30 grams per mole. And so this one is 180. So we just take that 180 and divide by 30 and we get 6. So we're going to have C6H12O6. So we just find that here. C6. We'll sit here for a little bit. Make sure you get that one. It's an important concept, even though it's only 2 problems. It's something that you need to know pretty well. You're going to come up against that one multiple times. Okay, let's balance an equation. So in this case, balance the following equation. So we have aluminum and 3 nitrates, 2 sodiums, and a sulfur. So we can work through this, and we can see that, well, right away we have 2 aluminums here. So we're going to need 2 aluminums there. Looking at those nitrates now, 2 times 3 is 6. So we're going to need 6 nitrates over here. So that was following the nitrates. That gives us 6 sodiums. And over here they come in pairs. So we need 3 of these molecules to give us the 6 sodiums. And then now we have 2 aluminums and we have 3 sulfurs, and so that all works out well. So we just need 1 of those. So that's balanced, 2, 3, 1, 6. And this is a way to ask you a question about balancing an equation. So you just give the list of coefficients in order. So this is the answer, 2, 3, 1, 6. So this is one of those situations where you may know how to balance a chemical equation, but you don't understand the question, right? And so this is why we do practice exams. So this is a different kind of question than you might have in Alex. So this is the way I would write this type of question on my exams. Balance the equation, and then just look at the answers and see what has all 4 coefficients. So this one has 2, 3, 1, 6, which is what you have in those blanks. Okay. So everybody cool with that? Because I would hate for you to know how to balance equations, but not know how to answer this type of question. You see the disconnect? And that's where a lot of times I think students get frustrated. They don't know what kind of style of question is going to be asked. You may know how to answer how to balance an equation. If I sat you down at my desk and said, balance this equation, you could do it. but then you get into the exam and you have trouble with the way the question is worded or constructed. So this is why I do a practice exam, so that you can look at this and go, okay, in that situation, this is the correct answer. Okay. All right. All right, now here's one's just straight up knowing the different kinds of reactions. So looking at this equation, it's not a combustion reaction. What would I look for if it was combustion? What splits up?
Yeah, like the
Yeah, so you're looking maybe for carbon dioxide and oxygen and some kind of carbony molecule, the fuel. So you need a fuel with oxygen. Were you doing decomposition?
I know it, like I knew what it looked like.
Uh-huh.
I just didn't know how to like word it.
Yeah, so in the combustion, you'll have a fuel with oxygen, O2, and then you'll have CO2 and water. And that would be your combustion. That's what you'd be looking for combustion. Decomposition sounded like what you were describing, something that breaks up. So like you might have calcium carbonate, and it breaks up to calcium oxide and CO2. So you got one thing that becomes multiple things. That would be decomposition. Single replacement, we saw those with the metal ones. So you might have a metal solid and like a aqueous salt. And then the solid metal becomes a cation, and the cation metal becomes a solid. So we're just replacing the metal that's in solution. That would be a single replacement. What are you looking for acid base? What's one of the products of an acid-base reaction in every case? Water. Yeah. So you're looking something that has maybe a hydroxide in it, and maybe something that has some acid protons, and then you're going to have water form. Okay. And some spectator ions, like a salt, sodium nitrate or something like that. So look for that water as a product for the acid-base reaction. Look for hydroxides as a reactant. Look for acid as a reactant. And then double displacement. So this is just where I call it like the dance partners, they swap. And so here we've got aluminum with nitrate, and now we have aluminum with sulfur. Here we have sodium with sulfur, and now we have sodium with nitrate. So they just change partners. The anions change partners, and the cations. So that's double displacement. And that's what we have in this reaction. Now, the only one, or there's maybe a couple more that aren't listed. Precipitation. I can't know if it's a precipitation reaction really unless I see what am I looking for? The states of matter. Yeah, I got to have like aqueous, liquid, something like that. But a precipitation reaction will have something in the product that's clear. It's a solid, right? It's precipitation forming a solid. So you have aqueous, and a solid and an aqueous. So that solid is the precipitate. You mix two aqueous things and something crashes out of solution and makes the solid. Redox. You're looking for something that has a change in number of electrons. Okay. All right, now we get into the calculations. So this is, yes. What's that? Oh, yeah, thank you. So if I'm doing this test, if I'm sitting down, you have 2 hours, so that was really nice. That helps. But still, I want to manage my time well. So I've hammered through all of these. Then I get to this page, okay, and I look at it. I see calculations. I see calculator work. So what do? Skip it. Skip. And I go on to find those ones, and I skip all the way down here until I get to ones that are no longer calculations. Well, it looks like all of them are calculations. But that's like, wait a second, there's an electron configuration. That's fast. So I'll do the electron configuration one. Okay, so manage your time well, too. So you go through a test, you do all of the ones that are fast. Not only that, but it builds confidence because you're going to know some of those. We hope, right? So you're going to nail those ones and you're like, all right, I'm making some points here. I'm doing pretty well. Now I've got a lot of time to go back to the calculations and work on those. So you don't get fixated on a problem and burn the whole test time on a single problem, because then you won't have time to do the easy electron configuration ones or things like that. Okay, so this, you've got to be mindful of the time. And so here we are. There are X molecules of methane and 0.123 moles of methane. So this is pretty straightforward. I've got to take that moles and do what with it? Whenever I'm going from moles to molecules or moles to atoms, Avogadro's number is the one to use, because that's the number of atoms in a mole or number of particles or molecules in a mole. So they just take that 0.123 moles and multiply by Avogadro's number, and I get the number of molecules. Okay, and so that's that answer. Again, I'm going to go fast so we finish. So it's on the video. You can write it all down. So it's 7.4. That's answer B. A combustion of ammonia in the presence of excess oxygen yields NO2 and H2O. The combustion of 28 grams of ammonia consumes X amount of oxygen. But let me highlight some things in this problem that'll help you. So when I look at this problem, I see that word excess oxygen. That means a lot. Okay. That means that ammonia is limiting. I'm going to run out of ammonia because I've got more oxygen than I need. Okay. So this means that ammonia is limiting. So I'm going to start with the mass of ammonia. I really don't have any choice because in this case I only have one number. I've got the mass of ammonia. But that excess oxygen is important. It's telling me that ammonia is going to run out. So then I go through and find the molar mass of ammonia. Nitrogen is 14, 15, 16, 17 for the 3 hydrogens. The grams of nitrogen or grams of ammonia have canceled. I get to moles of ammonia. I did you a favor here and balanced the equation for you. So it's a 4-to-7 ratio. So the 4 moles of ammonia cancel, and I get into moles of oxygen. Each oxygen atom is 16 grams per mole, so the total molecule is 32 grams per mole. So the moles of oxygen cancel, and now I've got grams of oxygen. I'm doing all of these in the shortest manner possible. I could do it, in the whole table or whatever, but this is the fastest way to do these problems. It's going straight down the column of ammonia and up the column of oxygen to figure out how much oxygen I need. Okay. So it's 94 grams. Okay. Hey, sorry, no problem. It was noisy out there, so I closed the door. Okay, so now we've got another one. This reaction of 4.73 grams of magnesium with 1.83 grams of water produces X amount of hydrogen. And here, what do you see in the problem? Do I see the word excess? No. Do I have a mass of both of my reactants? Yes. That means I have a limiting reactant problem. So whenever I see a mass of both reactants, I don't know which one I'm going to run out of. So the way you do this is you just start with one and convert it all the way over to the other one to see if you have enough or if you have too much. Okay. All right. So we're going to just start with magnesium and go all the way to water. So both masses of both reactants are given, therefore it's a limiting reactant problem. So I'm going to go from magnesium down the magnesium column, if you're picturing the table, down the magnesium column, and then up the water column, the other reactant, and see how much reactant I need. Okay. And so I've got magnesium, I get out of that into moles, the 1-to-2 ratio, and then into mass of water, and I end up with 7 grams of water needed. Okay, which is a problem because I only have 1.83 grams of water. So that tells me the water is going to run out before I run out of magnesium. So if I want to calculate the yield, the theoretical yield, which is how much hydrogen could be produced, I need to use the water. So I'll redo the whole problem starting with water. So I start with the water mass, get out of mass into moles, 2-to-1 ratio to hydrogen, okay, and then into the mass of hydrogen, and I've answered the problem. So this is the theoretical yield because I'm going to run out of water and I'll still have excess magnesium left over. So that's a limiting reactant problem in the shortest possible time and amount of calculations. I know I did a lot of stuff with the tables, and that's really a good skill to use if you're doing your own work on your own time, you know, but if you're in an exam, this is the fastest way to do it. If you end up in the exam and you want to just guarantee that you got it right and you're really comfortable with the table method, you can do that, maybe as a check on your work. Any questions on this one? It's probably the longest question on the test. Okay? Because the limiting reactant problem, first you have to figure out which one is limiting, and then use the limiting one to calculate the theoretical yield. Why am I calling this the theoretical yield? How many different yields are there? Actual, percent, and theoretical. The theoretical is the maximum. That would be if I completely ran out of all the water. But nature's hard. It doesn't always go to 100%. You know, as this reaction goes, the water has a harder time finding the magnesium. And so it may go to 90% yield. And if it got to 90% yield, it wouldn't be 0.1 grams, it'd be 0.09. It'd be 90% of that number. So this is the maximum. And then the actual yield might be 0.9. In fact, the next question is it's 0.8. So this reaction actually produced 0.08. Where is it? Right here, 0.08 grams of hydrogen. So what's the percent yield? Well, the percent yield is the actual over theoretical. So A is actual. And the theoretical here is this one. Times 100% gives us the percent yield. And so that's 78% or close to 80% yield. So these are two problems that are related to each other. That's the only downside of this on the test, is that it's kind of double jeopardy, right? If you miss this one, you're going to miss that one. Okay. And I try not to do that a lot, but you know, sometimes it's got to be done. So any questions? Okay. Okay, and then this last one is just a straight up question about spectator ions. So here's an example of an acid-base reaction. Let's go ahead and write it out just for grins. So I have KOH plus HNO3. And you see this OH here? That's the hydroxide, that's the acid proton. They're going to combine to make water. And so that's aqueous, water's liquid. This was aqueous, and this was aqueous. So I don't see a solid anywhere, so it's not a precipitation reaction, but I see that water as a product. So if I were to classify this one, it would be the acid-base reaction. It's an acid-base reaction that produces that water. And the potassium was a cation here, and it's a cation here. The nitrate, after it got rid of its proton, is a nitrate, and it's a nitrate here. So they're spectator ions. They haven't changed at all. The reaction took place between the H plus and the OH minus. So this is the OH minus and the H plus, forming the water. So here we are, that's the K plus and the NO3 minus. Okay, so then we have some dilution and solution calculations. So what's the concentration of methanol in a solution prepared by dissolving 11.7 grams of methanol in sufficient amount of water to give 230 mils of solution? So I did kind of shorten one step in this problem. But molarity, the concentration that we want, is moles of the solute per liter of solution. And so here we want to convert that grams of solute into moles, and then we want it in liters of solution. So instead of doing a whole conversion for liters, I said 230 milliliters, there's 1,000 milliliters per liter. So I just moved that decimal place over 3 places and made it 0.23 liters. So 230 milliliters. So essentially I divided it by 1,000 milliliters per liter. Hopefully that doesn't give you a headache. And so I end up with the molarity of 1.59. Any questions on that? You see how fast you have to be on the molar masses? You need to be able to just put those together like crazy. Okay, so that's again oxygen 16. You got 4 hydrogens, so that's 20, and then you got 12 for the carbon, so that's 32. Now we have a whole lot of decimal places up here. We don't need all of those for my tests because the answers are far enough apart. Okay, so I can do 12 for carbon, I can do 1 for hydrogen, and I can do 16 for oxygen. Okay. The only time that can be a problem is when you get to chlorine. You look to chlorine, it's 35.45, so it's right at a half. So I would do 35 and a half if you had a chlorine. But that's one of the few that you really have to mess with. Sulfur's 32. Phosphorus 31. It's pretty easy. Yeah, the chlorine is the only common one that you really need to have the half. Okay, everything else you can pretty much use whole numbers and get the answer. Okay. All right, now this one is so simple, but it tricks people. Okay. So it's how many moles of bromide ions are in 0.5 liters of a 0.3 molar solution of aluminum bromide. So they've got 0.5 liters, so that's pretty easy. And they've got the concentration here of 0.3 moles per liter. So it looks like you just take 0.5 times 0.3, but we're asking about bromide ions, not about aluminum bromide. And so this is the step right here that people forget and they get it wrong. So we're not asking about aluminum bromide, we're asking about just the bromide ions. And every unit of aluminum bromide gives me 3 bromide ions. So I've got to take that number of moles and I've got to multiply by 3. And so I end up with 0.45 instead of 0.15. So if you were to just do these 2 steps right here, you'd get 0.15 and you'd see, oh, wow, there's the answer. I got it right. No, you didn't. Okay. You got to multiply that by 3, and this is the answer over here. Okay. So be confident. Don't just do a quick calculation on your calculator and look at the letters and say, oh, there's one of the numbers that matches what's on my calculator. Okay. You got to know what you're doing in order to get it right. Okay, so here we have a dilution question. So we see this word diluting. Okay, so this sort of governing equation for dilutions, M1 V1 equals M2 V2. So that's the molarity times the volume of that molarity equals a new molarity and a new volume multiplied by each other. And so in this case, we want to know the concentration, or V2 or M2. And so that's equal to M1 times this ratio of V1 over V2. And let's see if I can identify all of those. So we're diluting this amount to a total volume. And so this is V1 here, and this is M1, and this is V2. So I have all of my numbers that I need, and I can solve for that. So this is V1 over V2, and this is M1. And I get M2. So dilution equations are great. You're typically given 3 out of the 4 things you need. Super easy, no tricks. Okay, and then we have a titration equation or titration example. You know, how many mils of this sodium hydroxide solution are required to neutralize this many mils of sulfuric acid, okay, at this concentration. So this one is also kind of a train. You start with, you know, a single unit of 35 mils because we want to calculate a single unit in milliliters. And so we just start converting. So we got 35 mils of sulfuric acid. Here's the concentration of that sulfuric acid. Here's the trick, though. It's 2 mils of this hydroxide to titrate the 2 protons in that sulfuric acid. So these two are connected right here. This H2SO4, since I've got 1 KOH here, 1 hydroxide, we could look at the balanced equation, H2SO4 plus KOH, and we're going to need 2 of those because we're going to form 2 waters plus a K2SO4. And so it's that 2-to-1 ratio that we need to take into account when we're doing the titration. And then we get out of moles of potassium hydroxide using the molarity, and we get to mils. So 62.4 mils. Okay, then we put in some thermochemistry. So what's the value of delta H for this reaction? Oh, it's given as minus 126 kilojoules. And so then we want to use that value. So if we have 25 grams of sodium oxide reacting with water, how much heat is released? And so here we start with the amount of sodium oxide. We get out of grams and into moles. And then we use that thermal value as a conversion. So we can get from moles to the heat. So 2 moles of this material here produces that much heat. Now the minus sign, whenever we use this word released, that can get rid of that minus sign. So it's 126 positive kilojoules are released. That minus sign means released. And so we can say 20.2 kilojoules were released by 25 grams of sodium oxide. Questions? Okay. All right, now we get into calculating the delta H of reaction from the delta H of formation table. I'm going to give you that same set of that same table that you had on the last exam. We had the bond energies and the enthalpies of formation, and it had an energy level diagram or whatever on it. That was just included in this practice test. All you really need is the delta H of formation table for this problem. And so here it is, here the standard enthalpies of formation. So for this reaction, we need to take the products and subtract the reactants. And so we have 2 CO2s. So it's 2 times that CO2 number. So here we are, CO2s, minus 394. Gives us negative 788. Then we have 4 waters, and you got to know which kind of water we're using. So it's this liquid here, the liquid water. And so that's the 286, minus 286 because it's liquid. Okay, 4 times that gives us negative 1144. And then we have to take apart the methanol. So here's the methanol right here. at 239. And this is a reactant, so we have a minus sign here, a minus sign here. Those cancel, and so we end up with a plus 478. And then this is one of those things that I'm sort of putting an extra little question in here. If you're looking at that table and you're like, I don't see oxygen, I can't do the problem. But by definition, oxygen is a gas at 1 atmosphere and room temperature, and so it has a delta H of formation of 0 kilojoules. So yeah, you could subtract your 3 reactants of 3 moles of oxygen, but it costs you 0 kilojoules to take that molecule apart and react it. Okay, and so here we are at the delta H of reaction 1454. So yeah, the only trick on this one was remembering that oxygen is 0, so it's not even listed in the table. We could look at that value and see that it's negative. We know that that reaction then releases heat. It's exothermic. Okay, which of the following is an oxidation reduction reaction? Okay, so we're looking at these. This one's just a double replacement. This one here is a precipitation reaction. Here's one. So I've got a silver nitrate and HCl forming silver chloride solid. So that's a precipitation. Double replacement, precipitation, PPT. Let's see, this is acetate, barium acetate, sodium sulfate. Oh, barium sulfate, that's a precipitation. So there's a solid there. And sodium acetate. Okay. And then this one down here is the acid base. So I've got an HCl and an NaOH forming water. And the spectator ions, chloride and sodium, are just staying in solution. And then this bottom one is a redox reaction. So this is also a single replacement. Because the copper solid has an oxidation state of 0, and over here copper nitrate has an oxidation state of 2+. And silver here has an oxidation state of +1. It's a cation in aqueous solution with nitrate, and here it's 0. So anytime those oxidation states change, we know we're gaining or losing electrons. So on this practice test, I didn't have the oxidation agent, the reducing agent, and so on. I guess I just ran out of space, but let's go ahead and practice that on this one because that's fair game too. And so first of all, let's ask those questions. What was reduced? And I'll say reduced. And oxidized. Oh my goodness, slow down. All right, so which one of these was reduced? The copper or the silver cation? So copper, what happened to its number? It went from 0 to +2. That's going up. And reduced, a good way to remember this is that number goes down. Okay, so silver went from +1 down to 0. The only way it can do that is to gain electrons. Oil rig, reduction is gain. But anyway, the nice way, the reduced actually works with the numbers. So silver is a +1, and it went down to 0. It was reduced. That number was reduced. So silver plus. So this actual species was reduced, the silver plus. Okay, silver cation. And then that means the oxidized was copper. Copper went from 0 to 2+, it lost electrons. Oxidation is loss of electrons. So Cu solid, that was That was the thing that was oxidized. Okay, then this means that the copper was the reducing agent. And the silver was the oxidizing agent. Yeah. So you find out what was reduced and oxidized first, and then that kind of changed the labels for the agents. Okay, so that's a little side trip. What is the correct ground state electron configuration for molybdenum? Well, we've got the periodic table here. Let's go find the trends. So we're looking at this. There's molybdenum right here. And this one is S1. That's group 1. This is group 2, S2. And then we get into the D block. So scandium is going to be S2D1. Then titanium group is D2. Vanadium group's D3. But we're getting close to D5. And so when we get to the chromium group, we steal an electron from the S and make a D5. And so molybdenum is going to be an S1D5. But what's the first number that we have? We come over here and we find that it's on row 5. Okay, and we go back and find that it's going to be the krypton core, and it's going to be 5s1, and then it drops down when you get to the D group to 4. So 5, 4. 5s1, 4d5. So it's this one right there. So all these others are wrong. We got a D10 here, that's wrong. We've got too many electrons on this one, so it's not the S2. This one has got, this is following the trend without the exception, so that's not right. And then here we got a 4D9, that's crazy. So there's something wrong with all those others too. Okay, formal charge on nitrogen in this ion, NO3 minus. Okay, so the number of valence electrons that nitrogen comes in with, right here, this guy, comes in with 5, but it can claim 4. So if we did sort of the equitable separation of the oxygens and the nitrogens, each one gets an electron for every bond. So nitrogen only can claim 4 electrons. And so you do the difference between those two, and you get a formal charge of +1. And then this is a great molecule to look at resonance structures, because I chose to draw the double bond in order to make an octet for nitrogen using this oxygen up here. But I could have just as well chosen this one, or I could have just as well made a double bond there. And so I had 3 options, and that's the 3 resonance structures that you have. So you see that, and I've shown the formal charges on all of those. The only thing I haven't shown is all of the extra lone pairs. Okay, but this is one possible resonance structure. This is the other possible, and the third. So you have 3 resonance structures. And then just sort of a simple giveaway, number of points. Right? How many valence electrons does NO minus have? So right here, it's got 5 for the nitrogen, plus 6 for the oxygen, plus 1 for the extra electron, as I'm making it a minus charge, and so that's 12. Okay, we're kind of out of time. Rats. We got 35. I'll go upstairs and I'll finish this video because we only got a few more left. And then you'll have a 2-part video, what we did in class and then what I did in my office. How's that sound? Okay? Yeah, sure.
And then we'll also meet on Wednesday, right?
Yeah, we'll meet on Wednesday. Actually, I can do the rest of this Wednesday. Yeah. Bring your questions so we're not bored.